The objective, determine the Bronsted-Lowry acid and base in a chemical equation. So, what are Bronsted-Lowry acids and bases? In a chemical reaction, we need to be able to identify the acids and bases without having to test the substances with an indicator. To do this, we can assume certain characteristics about acids and bases, and we'll give them some fancy names. So, a Bronsted-Lowry acid is going to be anything that's a hydrogen ion donor. We also say a proton donor instead of hydrogen ion because an H+ ion is essentially a proton. After an acid donates a hydrogen, what you have left over, the result of that transfer, is a conjugate base. And then together they form a conjugate acid-base pair. A Bronsted-Lowry base is going to be a substance that is a hydrogen ion acceptor. And so we also call that a proton acceptor. So the hydrogen donates, the base accepts or receives. After a base accepts a hydrogen, the result of it is a conjugate acid, which together they form conjugate acid-base pairs. So we're going to identify the conjugate acid-base pairs in several examples. And remember, all conjugate acid-base pairs only differ by one hydrogen. So the first thing we'll do is we'll notice we have our reactants on the left, our products on the right. And what I want to find is my conjugate acid-base pairs. They should only differ by one hydrogen. So if you'll notice, HCl and Cl- are conjugates of each other because they practically look identical, but they only differ by the fact that this has the hydrogen, but this does not. So these two are a conjugate acid-base pair. Now, who's the acid? Who's the base? Well, the one with more hydrogens is able to donate a hydrogen. So this is going to be my acid, which is the hydrogen donor. And this is going to be my base, which is the hydrogen acceptor. So if this donates a hydrogen, it's going to lose a hydrogen and it's going to become this. If this accepts a hydrogen, it's going to gain a hydrogen and then become this. So that's how they are conjugates of each other. All right, the other pair are going to be, hopefully it's obvious, the H2O and the H3O. They only differ by one hydrogen, so they are conjugate acid-base pairs. Which one's the acid, which one's the base? Since this has more hydrogens, it's got more to donate, so it's going to be the acid, the hydrogen donor. And then because this one has less hydrogens than this, it's going to be the acceptor. So that makes it the base, the hydrogen acceptor. And so the way we would answer this is a couple of ways. You might be asked to label the acids and bases, and you'd say from left to right we have acid, base, acid, base. Or you might be asked to identify the conjugate pairs, in which case this is a conjugate pair and this is a conjugate pair. Or you might be asked, if you have the acid HCl, what is the conjugate base? And you would have to know, well, if it's an acid, it's going to donate a hydrogen, and then after it donates, what it becomes is, in fact, going to be the base. So those are about 3 different ways you might be asked to answer questions about something like this. All right, let's look at number 2. So number 2, identify your acids and your bases. So since these are conjugates of each other, right, and then these are conjugates of each other. Now that I know my conjugate pairs, which ones are the acids, which ones are the bases, between these two, this has more hydrogens, so it's the acid and this is the base. And then between these two, this has more hydrogens, so it's the acid and this is the base. But this should check out because if it's an acid, it's a hydrogen donor, and if it's a base, it's a hydrogen acceptor. If we keep in mind our definition that this, if it donates one hydrogen, it's going to change into OH minus. If this donates a hydrogen, it's going to lose one of these 4 and drop it to 3, and it's going to become NH3. Also, notice we're losing a positive, so that's why this was positive and then it becomes neutral. And then same here, we're losing a positive when we donate a hydrogen, that's why this results in a negative charge. Okay, let's identify the conjugate acid-base pairs here. This one is paired with this one. See how they are the same except they only differ by one hydrogen. And then these two are conjugates of each other. They are the same, they only differ by one hydrogen. So now let's label our acids and our bases. In this pair, This one has more hydrogens. It must be the acid, which makes this its conjugate base. Remember, an acid is a hydrogen donor, a base is a hydrogen acceptor. So if this acid donates a hydrogen, what does it become? Instead of having that H there, now it's NO3. Instead of being neutral, now it's a -1. And then between these two, who has more hydrogens? Who can be the donor? That's this one. It's going to be the acid. This is going to be the base. Notice, if this donates one hydrogen, it goes from H3 to H2O, and it also loses a positive. So donating a hydrogen will change it from this to its conjugate base, H2O. Similarly, or reverse, if H2O accepts a hydrogen, because bases are a hydrogen acceptor, accepting a hydrogen would take it from H2O up to H3O plus. So that is how we can verify that we labeled it correctly. Now you pause the video and try to label the conjugate acid-base pairs here, and then you can unpause the video and check your answers. Now we're ready to check your answers. So first, here are my conjugate pairs, HCl to Cl negative, and here's my other conjugate pairs, OH minus to H2O. My acids and bases, this is my acid, this is a base, this is an acid, this is a base. And then number 5 is going to be, these two are my conjugate acid-base pairs, and these two are my conjugate acid-base pairs. And then to label, we have this acid first. After it donates, it becomes this, its conjugate base. And then this is going to be my acid, H3O plus, and after it donates, it becomes this, conjugate base. Now let's talk about neutralization reactions, which are acid-base reactions. An acid and a base react to produce a salt and water, which means they neutralize each other because salt and water are both neutral, as opposed to an acid having a pH less than 7, a base having a pH greater than 7. Well, now you have something that is pH equals 7, neutral, when you put them with each other. So it's like an acid cancels out a base. These are called double replacement reactions. So all neutralization reactions are acid-base reactions, and they are double replacement reactions. But just remember, not all double replacement reactions are neutralization reactions. If you spill liquid Drano while trying to unclog your sink, what would be a good household product to use to neutralize it? Well, liquid Drano, sodium hydroxide, is a base. So you want to find an acid to neutralize it. Find the opposite. A weak acid would be safer, something like vinegar. Hydrochloric acid is used to disinfect swimming pools, so that's an acid. If you spilled the hydrochloric acid, what would be a good household product to use to neutralize it? You want to use the opposite, a base. And a good household base would be some baking soda. When predicting the products, hydrogen joins with hydroxide to make water, HOH or H2O. The other two elements also combine and they form the salt. Remember that you always write the cation before the anion and then crisscross charges. So remember, double replacements, they go first and last. So hydrogen and hydroxide make my water. Third and second, Na and then Cl is going to make my salt. And then this is +1 -1 cancels. That's why it's just NaCl. So that's my water. There's my salt. You'll often be asked, what is the salt in this neutralization reaction? And so that's how you can tell. In number 2, first and last, hydrogen and hydroxide, that makes your water, right? Third and second are going to make your salt. Third is magnesium followed by sulfate. And then the charges are +2, -2, and that's how we have just MgSO4. Any ionic compound, it can be called a salt. So this is the salt in this neutralization reaction. Fun fact, magnesium sulfate is Epsom salt. So now let's practice a couple of neutralization reactions and then unpause the video to see the answers. So number 1, we're going to do first and last. So hydrogen and hydroxide, HOH, that's water. Okay. Then we're going to do third and second. So third is potassium, second is fluoride. Lastly, we have to go look up the charges of each of them on the periodic table to make sure that they are balanced. So the charge of potassium, it's here, is +1. The charge of fluoride is -1. So +1 and -1 cancel with each other. So this is just going to be HOH plus KF. If we look at number 2, we have first and last. This time that makes our salt, right? So first is aluminum and last is this sulfate, SO4, plus third is hydrogen, second is hydroxide. Hydrogen and hydroxide make our water. Okay, so now I need to verify the charges for my salt. And the aluminum is easier to find because it's right here on the periodic table. It has a +3. But this sulfate, I'm going to have to go look at my polyatomic ions list, which is here, polyatomic ions. And sulfate has a charge of, there it is, SO4 has a -2. So this is a +3, this is a -2, and now I have to balance the charges. This, crisscross them, means I need to have a 2 here, and that means I need a 3 down here. And of course, the point of crisscrossing is to balance the charges. 3 times 2 is an overall +6. 2 times 3 is an overall -6. And so finally, you might be asked to identify the salt in each. This would be your salt in number 1. This would be your salt in number 2.